So, what were we? We were dealing with sodium iodide. This is soluble, uh, easily soluble in water because there are no advantages. We have a uh, hard soft character here, and hard is okay, and soft hard, there is nothing to be gained. Uh, but if you have um, if you would have silver iodide, is that soluble in water? Does this form? Then we'll see. Then we would have here is a soft acid and a soft base. This is good. Um, and here is a soft acid and a hard base. This is questionable. Soft base and a hard acid. This is also questionable. So this is not soluble, even though silver plus and sodium plus or potassium plus, they are very similar in size and charge. Well, maybe the silver has slightly higher effective charge, or considerably higher, in fact. But at least there are a lot of similarities, and the differences between, say, the differences between. Sorry. My computer is mad. The difference between hard acid and hard base, that is okay, but soft acid and soft base, they can't be replaced by interactions from hard acids on hard bases. So for example, here we see a diagram of the equilibrium constant, uh, formation constant for soft acids and soft ions. When one increases the hardness, here is a hard anion, then the mercury compounds become less and less stable. And this should be mercury 2 plus is a typical soft ion, while scandium 3 plus aluminum is a typical hard ion. So for fluorine, they form strong complexes with soft ions and bases. They form less strong complexes. And this is perhaps, I mean, it's not, there is a trend, yes. And you can classify and motivate why some reaction are driven far away to the right, or not far away to the right, by attributing this hardness and softness character to the constituent ions. Well, finally, in the chapter, they speak a little bit about solvent leveling or solvent flattening, or how to say. Depending, if you use, here are some strange acids, HF and um, sulfuric acid, they are well known. And sulfuric acid is a strong acid, and while HF is a weak acid. At least that is what is the case in water. For if you have a water solution, then these effective pH from 0 to 14 approximately is reachable. If you change the solvent to ethanol, then you can reach other type of limits in effective pH, and perhaps sulfuric acid and hydrofluoric acid, they in some mixtures they could very well be more or less similarly strong. They could both be a strong acid. I think this is in um, you can use anhydrous hydrofluoric acid, and in that respect, sulfuric acid is not a strong acid if you dissolve sulfuric acid in hydrofluoric acid. But that is solely dependent on the fact that you stay away from water. Hydrofluoric acid is perhaps not the most nice solvent that you would like to have. And even so, this fluorosulfuric acid or the antimonofluoride, which is behaving, you can create environments that have an effective pH as -31 or something like that. This is terribly nasty to work with, and you need very special equipment. I think there nowadays are better alternatives to these super acids, they're called. It is, of course, impossible to have an effective pH of -31 in any solvent, but the reaction conditions can be such that it appears that the pH, one can model it as a solution with an effective pH very, very far down, more far down than can be attained in water. Actually, one replaces the normal pH concept by a Hammett acidity function, but in water the Hammett acidity function and pH is approximately the same. But in other solvents, one should perhaps speak about the acidity or Hammett acidity and not the pH, but yeah. Ammonia or DMSO is perhaps a reasonable solvents, and there you can have very, very effectively very basic environments. Compared to water, maybe at least 10, 15 orders of magnitude more basic, and you can probably dissolve stuff in DMSO and ammonia that is not at all possible to dissolve in water. For example, one can dissolve alkali metals in ammonia, and they are not extremely stable, but you can sort of work with them. Depending on what kind of solvent, a certain solute will show different type of properties, which is not surprising in a way. Ethanoic acid, that is this is quite easily handled, and it's toxic, but you can without problem work with it in the laboratory. Here you can reach pH, effective pH values that are quite much lower than possible in water, and the acid-base system, they are somehow different in ethanoic acid because the equilibria between the ethanoic acid and the ethanoate ion, as the self-dissociation is called, is not at all that the same as in water. The properties of anhydrous ethanoic acid are quite different from water. But if you dissolve the ethanoic acid in water, then it behaves according to water, the dominant solvent in that system. But if you have or metanoic according to this figure, you should be able to have very much more acidic species solved without possibly showing their acidity as acids. You can probably dissolve sulfuric acid in metanoic acid um, as neutral molecules, definitely in HF. I don't know what if you're working with these stabilizing very acidus species, carbocations, for example, is something that one can use these super acids for keeping them in a solution and doing experiments with them. Yeah, that was my view graphs. I was going to show a program also, Medusa.